The most common ways to make ethers is through the Williamson ether synthesis. This is a reaction where we turn an alcohol into an alkoxide by adding base, and then we do a substitution reaction on an alkyl halide. For example, cyclohexanol, when we add sodium hydride, which is a base, the sodium hydride will remove the hydrogen on the alcohol to make an alkoxide ion, which is a much better nucleophile than the alcohol. Then if we add a sterically unhindered alkyl halide, such as methyl iodide, we can do an SN2 reaction where the oxygen attacks the carbon with the leaving group, and as a result, we complete the reaction with an ether. Notice that because this is an SN2 reaction, we want to avoid sterically hindered alkyl halides. So this reaction is best to use primary methyl alkyl halides. Using tertiary or even secondary alkyl halides will often lead to E2 reactions. We also don't want a lot of sterics around the alkoxides for the same reason. In this question, we're going to try to come up with a Williamson synthesis of the following two ethers, methylpropyl ether and anisole. In order to make the following two ethers, we want to think about the Williamson ether synthesis being an SN2 reaction. If we look at the first example, the first question, we have methylpropyl ether, where we have two sterically unhindered alkyl groups around the ether. So that actually gives us two options for answering this question. We can add the methyl group by attaching a bromide, which would mean the alkoxide would have the propyl group. We can reverse that as well, where the propyl group is attached to the halogen, and the alkoxide comes with the methyl group. In the case of anisole, which is methylphenyl ether, we only have one option to make this ether, which would be having a methyl group attached to the halogen, and then the alkoxide would be this phenoxide ion, where the phenyl group is attached to the oxygen. If we try to reverse this, where the phenyl group is attached to the halogen, this reaction will not work since, remember, in an SN2 reaction, the electrophile can't have a phenyl group. The nucleophile would have to get inside of the ring to do an elimination or backside attack of the halogen. So if we had a halogen here instead of an oxygen, this reaction would not work. In this question, we want to rank the following alkyl halides in terms of reactivity in the Williamson ether synthesis. To answer this question, we want to think back at the requirements for an SN2 reaction, in particular the electrophile. You might recall that the best electrophiles are those that have a good leaving group and also have a sterically unhindered alkyl halide. Looking at the first question, we have bromoethane, which is a primary alkyl halide, which is really good for SN2 reactions. We have 2-bromopropane, which is a secondary alkyl halide, which is not as reactive as a primary alkyl halide. And then we have bromobenzene, which is not a good partner for the SN2 reaction, since the benzene ring will prevent a nucleophile from attacking the backside of the leaving group and eliminating that leaving group. As a result, bromobenzene is the least reactive, bromoethane is the most reactive. In the next question, we have chloroethane, which is a primary alkyl halide, bromoethane, which is also a primary alkyl halide, but it has a better leaving group than chloroethane, and then 1-iodo-propene, which is a compound that has a halogen attached directly to the double bond, so it's a vinyl alkyl halide. These are not good for the SN2 reaction. So this 1-iodo-propane would be the worst electrophile or least reactive electrophile. Chloroethane would be the next least reactive, and bromoethane would be the most reactive alkyl halide in this group. Another reaction to make ethers is the alkoxymercuration. This typically starts off with an alkene, and we add a mercury reagent plus an alcohol to make an ether. This is very similar to the oxymercuration, which we learned about previously, where an alkene is treated with a mercury reagent plus water to make an alcohol. The reaction that we're about to cover, the alkoxymercuration, works well with primary, secondary, and tertiary alcohols. It starts off with an alkene, for example, styrene. We typically add mercury trifluoroacetate and then an alcohol. So in this case, we're using methanol. That leads to a Markovnikov addition of the alcohol. So the alcohol goes on the more substituted carbon of the double bond. The mercury trifluoroacetate adds to the least substituted carbon. Then sodium borohydride, through a mechanism we won't go into, will replace the mercury with a hydrogen. Overall, this reaction produces the Markovnikov ether from the reaction. Here's a second example with a symmetrical alkene. We're using mercury trifluoroacetate and ethanol, followed by sodium borohydride, produces a ethyl cyclohexyl ether. Notice that in this reaction, we're using mercury trifluoroacetate. This is very similar to the mercury reagent we use with the oxymercuration. In that case, it was mercury diacetate. So in this case, mercury trifluoroacetate simply replaces 3 hydrogens on this carbon with 3 fluorines. Both reagents essentially do the same reaction. This one just happens to work a little bit better, as shown with these examples. Here's another example with an unsymmetrical alkene. We're using mercury trifluoroacetate plus methanol, followed by sodium borohydride to produce the Markovnikov product. Notice the ether attaches to the more substituted carbon. The ether can be predicted just based on the alcohol we're using. So methanol was used here. So we get a methoxy group being added. The mechanism is very similar to the oxymercuration. It starts off with the alkene attacking the mercury, which is a metal. It's electrophilic. The pi electrons in the alkene make it nucleophilic. After the mercury is attacked, one of the trifluoroacetate groups is eliminated. And then at the same time, the d orbital electrons from the mercury attack the developing partial positive charge on this carbon, the more substituted carbon. This produces an mercurium ion. Notice we have seen this before. So this is a 3-member ring with mercury as part of the ring, and mercury has a positive charge. It's a very electrophilic ring, so methanol, which is not the best nucleophile, will attack one of these 2 carbons. Usually it attacks the more substituted carbon. The reason for that is there is more of a partial positive charge on this carbon than there is on the less substituted carbon. So think of this as the bonds between carbon and mercury being partially broken, and that develops a positive charge or a partial positive charge on the carbon here, similar to a more substituted carbocation. There is more of a concentration of a positive charge there, so that is where the methanol adds. In the next step, this hydrogen from the methanol is removed, by a base in the reaction, we could use, for example, the trifluoroacetate, which was eliminated in the first step of the mechanism. This leads us to the last intermediate, where a methoxy group has added to the more substituted carbon, and a mercury trifluoroacetate group is on the less substituted carbon. And then lastly, sodium borohydride will replace this mercury group with a hydrogen. This question asks us to prepare an ethyl phenyl ether with phenol using the Williamson ether synthesis as well as the alkoxymercuration reaction. To make ethyl phenyl ether from phenol, we could use the Williamson ether synthesis by adding base, so sodium hydroxide or sodium hydride will do the same thing. The base will deprotonate the hydrogen on the phenol, make it more nucleophilic. And then if we add an ethyl group with a halogen as a leaving group, we can get the ethyl phenyl ether product that we're looking for. Another way we can do this reaction is through the alkoxymercuration reaction, where we use mercury trifluoroacetate and an alkene. If we're trying to add 2 carbons, our alkene will have to also have 2 carbons. And then finally, we add sodium borohydride to remove or replace the mercury group that is in the intermediate with the hydrogen.